Alright, in this video, I'm going to be talking a bit about cosets. So if G is a group, and H is a subgroup of G, and then let's say that little g is an element of the group big G, okay? So here I define two sets. So the set GH is defined to be the set of all elements of the form GH, where H is an H. And similarly, HG is the set of all elements of the form HG, where H is an H. Okay, so essentially, to get the set GH over here, you take every element of H and multiply by G on the left. To get the set HG over here, you take every element of H and multiply on the right by G. So this guy, GH, is an example of what we call a left coset. So it's a left coset of H and G. Likewise, this guy over here, HG, is an example of a right coset of H and G. So every element of the group will give you a left coset and a right coset just by multiplying H on the left or on the right. Okay? Here I quickly summarize some facts about cosets. So the first fact that I mentioned here is that for any two elements G1 and G2 in the group, either the cosets G1H and G2H coincide, or the cosets are disjoint, okay, meaning that their intersection is empty, they have nothing in common. Now here I've stated this for left cosets, but the same is true for right cosets as well. Okay? The next fact that I stated was that the left cosets of H form a partition of the group G. And the same is true for the right cosets as well. So if you'll remember what a partition is, basically what we're saying is the cosets are all disjoint. So that's kind of what I talked about in the first fact already. And that the union of all the cosets gives you the entire group. So that's what I meant to partition the group, okay? The last fact that I decided to mention is that all of the cosets of H have the same number of elements in them. Using some terminology from TCAL, you can say that they are all equinumerous. And in fact, they are all in bijection with H, or if you will, they all have the same cardinality, or the same number of elements as H, okay? There are some other facts about cosets, which I could probably list, but I think I would just leave it at these three for this video, okay? What I'm going to do for the rest of the video, though, is just some examples of computing some cosets of subgroups in various groups, okay? So for the first example, let's consider our group G to be the group of integers. The operation is going to be addition. And then for our subgroup H, let's take the subgroup consisting of all of the integer multiples of 5. Okay. So H, but I list all the elements of H right now. So all integer multiples of 5. So negative 15, negative 10, 0, negative 5, 0, 5, 10, 15, and so forth. So that's like a little snapshot of all the elements in the subgroup H right now, okay? So if I want to find all of the cosets of H, okay. So what do I want to do? To get a coset, I want to take an element of my group, and I just want to apply it to every element in my subgroup. So let's see here. Let me take a number that's not in H right now. So I see that the number 1 is missing. So let's take the number 1 and let's see here. The group operation is addition. So let's try adding 1 to every element of H right now. So then this will give me a coset of H. And I'll list some of the elements in this set. So all I'm doing is adding 1 to every element in H. Okay. So that would have been one of the cosets of H right now. Okay, so I don't have all of the integers yet in these two cosets. So looking at it, there's still quite a few integers that are missing. So that means I'm not finished yet. There are some more cosets that I have yet to discover. So to get another coset, what I will do is take another integer that's missing. So for instance, I notice that the number 2 is missing right now. So let's take 2 and add it to everything in H. Okay. So I'll list some of the elements in this coset. So I'm taking all these numbers here, I'm just going to add 2 to all of them. Okay, so that's another coset of H. So do I have every integer right now? So the answer would be no, I'm still missing a few integers, right? I have 0, 1, 2, but we don't have the integer 3 anywhere. So I have at least one more coset that I need to list. So let's do 3 plus H. And again, I'll list some of the elements of this coset right now. So if I just add 3 to every element of H, so here are some of the elements in this coset. And again, I'm just adding 3 to every element in H. Okay. Alright, now do we have all of the elements yet? The answer is no, okay? So notice that I'm still missing the integer 4 right now, okay? So let's use 4 to get another coset. Okay. So I'm just going to add 4 to every element of H. Whoa. Okay. So now let's see, do we have all of the integers now? So if you take a close look, we do. So we have the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. You can also count backwards if you want. So we have negative 1, negative 2, negative 3, negative 4, negative 5. we have -6, -7, -8, -9, -10, and so forth. So we have all of the integers covered, and once we see that we have all of the elements of our group in at least one of the cosets, that's when we know that we have found all of the cosets, okay? Now you can observe a couple of things right now. So one thing that I mentioned was how the cosets are going to be disjoint from each other. So notice how none of these cosets have any number in common. Okay. So these 5 cosets that I have here partition the set of all integers. So every integer appears in exactly one of these cosets. Now here I computed the left cosets of H, but of course since G is abelian, the left cosets of H happen to coincide with the right cosets as well. If your group is not abelian, then it will not be the case that the left and right cosets coincide. Not necessarily, okay? All right. Now, if I were to take like the integer 5 right now, so I've already found all the cosets, but just to illustrate, what if I take 5 and I multiply it, or I add it to H, okay? So taking 5 and adding it to everything in H, well, notice that it's basically just giving me, all the multiples of 5 again. So 5 plus H is really the same as H itself. So that's kind of reflecting what I talked about in the first fact here, that for 2 elements of your group, they might produce the same coset. So 5 and 0, if you will, give me the same coset. But if they don't give you the same coset, then instead the cosets will be disjoint, all right? Okay, so I'll just do a couple more examples. This may be worth noting real quickly before I do another example. If you consider just the integers in general, and then if you take the subgroup consisting of all multiples of n, you would find that there are n cosets of H in G. Analogous to how in this example for the subgroup 5Z, I found 5 distinct cosets. Okay? All right. Let's do another example. So now let's take the group G to be a subgroup of the integers. So let's consider G to be the set of all integer multiples of 2, or if you will, the set of all even integers, okay? And let's take H to be the set of all multiples of 8, okay? So again, G is all the even numbers. Whereas H is all of the multiples of 8. Okay, so certainly every multiple of 8 is an even number. So H is in fact contained in G, so it's going to be a subgroup of G, okay? And we want to find all of the cosets of H right now. So certainly one of the cosets is going to be H itself. So that would be the coset corresponding to adding 0 to every element of H. And again, it's often helpful to write out some of the elements of the coset. Okay, so do I have all of the numbers in my group accounted for? So the answer is no. I'm missing numbers like 2 and 4 and 6, for instance. So let's take one of the numbers that I'm missing. I'll take the number 2. So let's add 2 to our subgroup H right now, okay? Now notice that I don't want to add the number 1 to H because 1 was not a number in my group G, okay? Since G is the group of even integers, then when I'm finding cosets of H, I would only want to use even integers to find the other cosets, all right? So to get this coset, I want to add 2 to every element of H, okay? So here I'm going to list a couple of elements of this coset. Okay. So then, to know if you have all of the cosets, again, you just need to check to see, do you have all of the elements of your group accounted for in the cosets? So I have the numbers like 0 and 2, but I'm still missing the numbers 4 and 6, for instance, right? So let's take the number 4, and let's add 4 to every element of H. So adding 4 to everything here. Okay, so these are some of the elements in the coset. So then again, I check to see, do I have all of the elements of G accounted for here? So the answer is no. So, because I'm still missing the number 6, for instance. Okay. So here I go from 0 to 8. I have 2 to 10, 4 to 12. So nowhere does the number 6 appear in any of these cosets. So let's take the number 6 right now and add it to everything in H. All right, so adding 6 to everything here, I'm going to get this. Okay. So do we have all of the cosets now? So looking at the cosets that we have listed, notice that now we do have all of the even integers. Okay? We have 0, 2, 4, 6, 8, 10, 12, 14, etc. You know, we have -2, -4, -6, -8, etc. So now that I see that we have all of the elements of our group accounted for, that tells us that we have found all of the cosets of H in G. Okay? Now, a bit more precisely, I have found all of the left cosets of H in G. Okay? But again, in this example, our group G is an abelian group. So the left cosets coincide with the right cosets, okay? Let's do another example. So it's going to be good to do an example involving a finite group. So let me take the group G to be the group of Z36. So it's like integers with addition modulo 36. And then let's take H to be the subgroup generated by the number 6, okay? So remember G, the elements of G, we can consider them to be the numbers 0 through 35. Okay? Now H is the cyclic subgroup generated by the number 6. So it will consist of all the multiples of 6. So 6 plus 6, 6 plus 6 plus 6, and plus another 6, and so forth. And then 30 plus 6 gives me 36, but 36 is equivalent to 0. So that would be all the elements of H, okay? And again, I want to start finding all of the cosets of H and G. So again, every subgroup is always one of its own cosets, because you can just multiply, or in this case, add the identity element to your subgroup. Okay. So to get some more cosets, take an element of your group that is missing. So the number 1 is missing. So I'm going to take the number 1, and the group operation is addition. So I'm going to add it to everything in H. So here is another coset of H right now. All right, now we have 2 cosets. Do we have all of the elements of our group G accounted for yet? The answer is no. So I have 0 and 1, but I'm missing the number 2. So we can take 2 and add it to everything in H to get another coset. Adding 2 to everything up here. Okay. Do we have all of the elements of G yet? Still, no. I'm missing the number 3. So I can take 3 and add it to every element of H to get yet another coset. I'm still missing the number 4, so let's add 4 to everything in H. So adding 4 to everything up here. Okay, are we done yet? Do we have all of the elements of G accounted for? The answer is still no. I'm still missing the number 5 right now. So let's take 5 and add it to everything in H up here. Okay, and now taking a look at all of the cosets that we have, you will notice that we do have all of the elements of G accounted for now. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way to 35, okay? So now that I have all of the elements of the group G accounted for, I now know that I have found all of the cosets of H and G, okay? Again, this group G was abelian, so I computed all the left cosets, but again, the left cosets happen to coincide with the right cosets. Okay. And if you take any other element of the group G and you try adding it to everything in H, the coset that you would get would coincide with one of the cosets that we have listed here. Okay? So these are all of the distinct cosets that you would have found in this example. Now here I want to maybe just make some observations. So first is that again, the cosets they're all disjoint from each other, right? The cosets in this list. So that is supposed to be the case. Unless your cosets coincide, they should have nothing in common. Okay? Again, your cosets altogether should cover the entire group. And that's how we've been determining whether we have found all the cosets yet or not. There's one other fact that I mentioned at the beginning that I want to highlight. So I mentioned that all of the cosets of H should have the same number of elements in them. You can see that clearly in this example here. Every coset of H has 6 elements in it, coinciding with the number of elements in H, which I guess happens because H itself is a coset. Okay? So the fact that this is always true, that the number of cosets or the number of elements in any coset is the same, and that the cosets altogether make up the entire group. That fact leads us to one of the important results in this class. It's known as Lagrange's Theorem. So if you take so let's say G is a finite group. So the number of elements in the group G. Okay, so one way to count the number of elements in the group G is to add up the number of elements in each of the cosets of H. But each of the cosets of H have the same number of elements in it, namely the number of elements in H. So that means that the order of the group G would equal the order of the subgroup H times the number of, and then maybe here I'll specify left cosets of H and G. Same is true if you replace left with right. So, that's just saying, like in this example, it's just saying that 6, the number of elements in H, times 6, the number of cosets that we found, equals 36, which was the number of elements in G altogether. Okay? And in particular, something very interesting that we note from this equation is that the order of any subgroup H must divide the order of the group G itself, okay? So if you have a group of order 20, okay, then every subgroup would have to have an order which divides 20. So the subgroups would have to have order 1, 2, 4, 5, or 10. Okay? So that's kind of an interesting result that we get, which is called Lagranges Theorem. All right, I'm just gonna do, I think, one more example. So let's do an example with permutations. So let's take G to be the group S3, and let's take H to be the subgroup generated by the transposition 2, 3. So it will be useful to list out the elements of G and H. So let's see here, 8G, well, let's see here, so the identity permutation is certainly one of the elements. Let's see here, what are all of the transpositions that we could have in S3? So 1, 2, 1 and 3, and then 2 and 3. Those are all of the possible transpositions in S3. And then we also have some 3 cycles, so we could have 1 maps to 2, and 2 maps to 3, and 3 maps back to 1. And then instead of mapping 1 to 2, we could map 1 to 3 instead. And then have 3 map to 2, and then 2 back to 1. And something that I talked about in my last video on permutations is that the order of Sn is n factorial. So the order of S3 would be 6, meaning there would only be 6 elements in S3. And so because I see that I already have 6 elements listed out, I know that I have found all the elements of G. Okay, so what about H? Okay, so certainly the identity is one of the elements of H. And then of course 2, 3 is an element of H. And then from my previous video I said that the order of a cycle was equal to its length. So 2, 3 being a transposition is a cycle of length 2. So it's of order 2. So it would only generate a cyclic group with 2 elements in it, so that would be it. Okay? All right. And now we want to find the cosets of H and G. So of course we could multiply H on the left by the identity, and that would just give us H again. So that is one of the cosets. Okay, so now we know that every other coset is going to have 2 elements in it as well. So we kind of see ahead of time there's going to be 2 other cosets in order to account for the 6 elements in G altogether. Let's take an element of G that is not in our first coset. Let's take the transposition 1, 2. And let's multiply every element of H on the left by the permutation 1, 2. Okay? So 1, 2 times the identity, of course that's just 1, 2. Okay, 1, 2 times 2, 3. Let's see what that would give us. So remember how we do this. We can start by taking any number between 1 and 3. Let's take the number 1. So what does 1 ultimately map to? So first, this permutation maps 1 to 1. So we'll take that 1 and plug it into this permutation, which will map 1 to 2. Okay. So where does 2 map to? Well, 2 will first map to 3, and then that 3 will map to itself. And we have all the numbers, so 3 would have to map to 1. You can confirm that's the case, but that gives us the other element of this coset, okay? Okay, now let's take another element of G that's not listed yet. We have 2, 3, and 1, 2, but we are missing the last transposition 1, 3 here. So 1, 3, multiplying H on the left will give us the last left coset. So of course 1, 3 multiplying the identity will give us 1, 3. And 1, 3 times 2, 3 must give us the permutation 1, 3, 2. Because that was the only element of G that was missing. So it would have to have gone there, okay? So these are all of the left cosets of H and G. But in this example, I mentioned it in my last video, S3 is not abelian. That means that the left cosets are not necessarily the same as the right cosets. So let's actually compute the right cosets for this example, which are not necessarily the same as the left cosets that we have found just now, okay? Well, one of the right cosets is going to be H itself again because you multiply on the right by the identity. Okay. Now let's see here. 1, 2. Let's try multiplying H on the right this time by 1, 2. So 1, 2 times the identity, of course, gives us 1, 2. Now we're doing, let's say 2, 3, and we want to multiply on the right by 1, 2. Let's see what that will give us. So starting with the number 1, 1 will map to 2, and then that 2 maps to 3. So next 3 will first map to 3, but then that 3 will then map to 2. And since we have all the numbers, that must be it, okay? So notice that 1 to H, this left coset, was actually different from this right coset, H1, 2. We're missing the transposition 1, 3 again. So multiplying H on the right by 1, 3 should give us the last coset. And we know that this last coset must contain the elements of G that are missing. So it will contain 1, 3. And then we're also missing the 3 cycle 1, 2, 3. Okay? So then this would be all of the right cosets of H and G. Alright, so that's just some examples of finding cosets of various subgroups in various groups. I think I will go ahead and end my video with that.